Law of signs. Objective here, we're going to learn and apply a new area formula that works with some triangles. And then we want to learn the law of signs, understand how and when to use it, find missing parts of non-right triangles. This is a tool that works for triangles that are not just right triangles. Those tools we have very well established. Pythagorean theorem and sine, cosine, and tangent do great with the right triangles, but not every triangle is a right triangle. So our bonus area formula that we want here is that in certain situations, if you have the appropriate information, then the area of a triangle can be found by doing 1/2 times A times B times the sine of theta. So the idea here is if we know A and B that are this side and this side, and we know the angle in between them, so this is like a side angle side situation in this triangle. Normally our formula for area of a triangle is 1/2 times base times height. We have the height marked in here, but when we draw that height, we actually get a right triangle. And if we know side A, which is the hypotenuse, and H, which is the opposite side from this, then we would be able to say that sine theta is equal to the opposite over the hypotenuse. We have to pay attention to what's actually in this picture. And so the height of this triangle is A times the sine of theta. And if we just replace this with A sine theta, then we have all the pieces that are in this formula. So we use the trigonometry to figure out what the height of the triangle is if we have the right kind of information. So to find the area of this triangle, we have the side angle side situation going on there. And so it says the area of that triangle will be 1/2 times 98 times 120 times the sine of 40 degrees. I make sure that my calculator is in degree mode for this because the angle is labeled in degrees. And I will do 1/2 times 98, or I could just say that's 49, times 120 times the sine of 40. And my calculator tells me that that is approximately 126.13 square units, whatever the units happen to be. So that's how we use that area formula. It's handy to have something other than just 1/2 base times height when you can't directly see either what the base is or what the height is. All right, so the heart of this, though, is about the law of sines. What the law of sines tells us is that for a triangle ABC, the sine of angle A divided by the length of side A will give you the same ratio as the sine of angle B divided by the length of side B, which will be exactly the same ratio as the sine of angle C divided by length of side C. Now in practice, we don't usually use all three of these. The idea is that hopefully between two of them, we know 3 of the 4 pieces of information. Okay? This works really well when you have angle side. That was one of our proofs that we could use to prove that 2 triangles were congruent, or if you have angle side angle. Okay? So, for example, if we're going to do this first one, I look in here what I have. I've got an angle and then an angle and a side, so this is angle side. This should work for that. I don't know anything about some of these. I'm going to go ahead and fill in everything that I know here. So I'll start with E. I've got sine of 38 over 75. Should be the same thing as the sine of 43 over side G is not labeled. and sine of f, which I actually know what f is, right? Part of solving the triangle is finding all of the missing pieces. And so these two things together add up to, what do we got? 38 and 43 is like 40 and 41. Those add up to 81. And 180 minus 81 is 99. So I know that that is 99 degrees. So I can say this is the same thing as the sine of 99 degrees over the length of side f. And so if I grab one of these, this one right here, that's a proportion. I can cross multiply and solve and figure out that the g is going to be 75 times the sine of 43 divided by the sine of 38. Those are in degrees, and that is what I'm going to put into my calculator. So 75 sine 43 and divide by sine 38. And I get 83.1 approximately. So that was for G. This is 83.1. That makes sense to me. It's a little bit bigger than the 75. The 43 is a little bit bigger angle than the 38. I would suspect that the F is going to be bigger still. So for the F, I'm going to ignore this one in the middle, and I'll do the sine 38 over 75 is equal to sine 99 over F. And when I do my cross multiplying on there, it's going to tell me that F is equal to 75 times the sine of 99 divided by the sine of 38. And that is what I will put into my calculator. So 75 sine 99 divided by the sine of 38. And it tells me that's 120.3. Again, bigger than the other ones. I believe that is an answer, and I now know all the sides and angles in that triangle. Okay. Let's do another one. Okay. So for this one, here is our triangle. I'm going to move that over there a little bit farther. Again, I know the two angles here. In fact, what I know is angle, side, angle on that. So that's one of them that was in my list before as usable for this. Again, these two angles add up to 128 degrees. And so 180 minus 128 is like 52 degrees left over for that angle up there. Okay, 78, I believe that. And so my proportions that I can write, I can say that the sine of 52 over 9 is equal to the sine of 102 over side I, which is equal to the sine of 26 degrees over side J. I'll grab this one and do my cross multiplication. The I will be 9 times the sine of 102 over the sine of 52. My other one, if I set it up and use the sine 52 over 9, and I want to keep using this one that gave me the apparently most accurate numbers. Nothing's been rounded in this one. Sine 26 over J, and that one's going to give me that J is equal to the 9 times the sine of 26 degrees over the sine of 52 degrees. You can put those things into your calculator. Actually, I'll just pause the video, do the calculations, and come back. All right, so those are the answers that I got. You hopefully verify that with your calculator. If you don't, then you know what questions you need to ask me later. So now we come to the pesky side-side angle, which was not one of our congruents. That's like, other than angle, 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 which was purely a similarity thing, this was the one that didn't work. And it couldn't work for a number of different reasons. Here's the basic setup of a side, and an angle that we might know up here. And various things could happen depending on just how long that side A is. If A happens to be exactly this distance here, then we're going to get just one triangle. If A is bigger than the value of B, then it definitely has to reach out this direction out here, and we could get some triangle out there. But if it's not bigger than B, then who's to say that that one didn't come in here and hit on that direction? And so what we need to know really as a deciding point is, what is this value? Okay? And if we know these things, and we call that theta, or we can just refer to it as A, we can come up with this number because that's the opposite side. B is the hypotenuse. So we could say that the sine of angle A here is equal to the opposite side, which is that side in red there, divided by the hypotenuse. And so this is B times sine A. And we kind of need to figure out what B times sine A is to figure out if we're going to get a triangle and how many triangles we might get. So one thing we can settle right off the bat: if the measure of angle A that they give us in this situation is bigger than 90 degrees and A isn't the longest side, then there is no triangle. Okay? There can only be one biggest angle in the triangle, and if we are 90 degrees or above, then the other ones have to be acute, and the biggest side has to be across from the biggest angle. So if A isn't bigger than B and the measure of angle A is greater than or equal to 90, excuse me, then we're never going to make a triangle. Okay. The rest of this, okay, our A has to be at least as long as B sine A. Okay, so if A is not as long as B sine A, then it's not going to reach all the way down here and make a triangle. Okay, so if A is smaller than B times the sine of angle A, then we have no triangle. If it's bigger, okay, and if it happens to also be bigger than B, okay, so if A is larger than B, okay, then there is only one triangle that we could possibly get. Okay? And so we can barge right into the law of sines and go crazy with it there. If it's not, if A is somewhere between B sine A and B, so if A is stuck between B sine A and B, then there are two possible triangles. Now, I don't know how often this happens. Probably happens more in a geometry book than any place else. Okay. But if that is the case, as we mentioned before, we don't know if this side went down here or if the side went down here, because these could be congruent and we would get two different looking triangles. So let's explore this in an example and see if we can come up with how to deal with it. Okay. So we have a triangle where A is 11, B is 17, the measure of angle A is 30. That's smaller than 90, so that doesn't help us eliminate and say anything. Okay, but we are going to need to test. If we were to, let's go ahead and just draw a generic triangle, and we'll label it ABC, and here's the 30-degree angle, and here is the 11, and the B is the 17 down here. If we were going to make it look a little bit more like one we did before, then we'll call that B, and we'll call that C, and this is 17, and our concern is what's going on with this thing. Okay, that is, we can see that we have side angle. Okay, rather than a check mark, we're going to put the exclamation point that reminds us that we need to figure out what B times the sine of A is. So that's 17 sine 30. Sine of 30 degrees from our unit circle special right triangles is a half. So this is 8.5. And so our 11 is between 8.5 and 17, which means since the 11 is between 8.5 and 17, there are two possible triangles that we need to consider. Okay, so let's go ahead and set up the law of sines here, okay, which is going to look like sine 30 over 11 is equal to sine B over 17. Okay, there's nothing else that we have in this point or can find at this point. All we would be able to say is that sine of angle C over the length of side C, but we don't know either of those. So we're going to cross multiply here, or multiply both sides by 17, and get that 17 sine 30 over 11 is equal to sine B. If we want to get to that B, we need an inverse sine. So B is going to be the inverse sine of 17 sine 30 over 11. And this is exactly what I'm going to type into my calculator. And I got 50.6 degrees out of there approximately. And I would be able to say for my first possibility, if B is 50.6 and A was 30, then the 50.6 plus the 30 gives me 80.6, if I can write correctly. And so that would say that the measure of angle C would have to be 180 minus 80.6, which would be 99.4 degrees. And then I could bring that up here and say, all right, I've got the sine of 99.4 over C that is equal to my sine 30 over 11. And that is going to give me C is equal to 11 sine 99.4 over sine 30, which I know is a half, but I'll go ahead and write it as sine 30 anyway. And when I do that, I get that C is approximately equal to 21.7, which makes sense. It was across, if it was a 99.4 degree angle, that's the biggest angle, and I would expect the largest side to be across from there. But the problem was here. Okay? And when I did the inverse sine of this, and as a decimal number, that is 0.77, the 17 sine 30 over 11. And if I go back to my unit circle, cosine comma sine, sines are y values. A y value of 0.77 is up here somewhere, okay, 0.77, and I know that that can happen actually in two different locations. The first one I just found was 50.6 degrees. That's what the calculator was able to tell me about. The other one is going to be over here and be 50.6 degrees as a reference angle that way. So that's going to be 180 minus 50.6, which is like 129.4. And so if C was actually, or B, if the measure of angle B was actually the 129.4 degrees. Okay. Then when I added on the 30 degrees here from angle A, that gives me a 159.4, and that leaves me 20.6, yeah, 20.6 degrees is the measure of angle C. And then I would be looking at a problem that looked like sine 30 over 11 is equal to the sine of 20.6 over C, which of course is 7.7 approximately. It's now the smallest side, so it doesn't surprise me that that I have the smallest angle across from the smallest side. So my two possible triangles, again, are ones you can pull off of here. Either angle B is 100 or angle B is 50.6 degrees, and it would look like this, and that would make angle C the 99.4, and it would be 21.7 across from it. Or if it's not that, then my triangle is going to look more like this, with my 30-degree angle here. My angle B was 129.4 degrees, and my side here was 7.7 because this angle was only 20.6 degrees. So unless I have some other information, I can't really tell the difference between those two. So if the information that you're given when you draw the triangle is angle, angle, side, then you got some work to do. Hopefully you have these notes handy for a while you learn how to deal with that.